So looking at number 7 on worksheet 2, actually you may start on the graph in case I need to draw on the graph or make some notes on the graph. The car is traveling on a straight road, 0 to 24 seconds. The car's velocity is modeled by the piecewise linear function defined by the graph on the right. Okay, so again, take an extra second to remind yourself or reiterate to yourself what you're looking at. Velocity, that's how fast the car is going. So before you even ask me questions, maybe I want to look and see. It's always positive. It speeds up until it gets to 20 meters per second. It stays at 20 meters per second, and then it slows down to 0. All right, now let's see if we can answer these questions. For each of v'4 and v'20, find the value or explain why it does not exist. Okay, well, v'4, that means derivative of v at 4. The derivative of v at 4.
Is it D&E because it's a cusp?
Correct. It does not exist because of a cusp. And at 20, v'4, D&E because of cusp. V prime at 20, so that's dv dt at t equals 20. Let's see. So at t equals 20, it's about right there. I want to know the instantaneous rate of change, the derivative of that line. Now this is maybe misleading because what's the instantaneous rate of change of that line equal to? Acceleration, true. How am I going to find it off of that graph though? How am I going to find the...
V is decreasing, but it's positive.
But how am I going to find the actual value of the derivative at that point? What is the derivative at a point? Okay, it's instantaneous rate of change. Give me another word. Slope at a point. Since this is a straight line, I can find the slope of this whole line. And this is what's maybe tricky. At this one point, well actually for this whole thing, the A rock and the I rock are the same since it's a line. Right. So be careful. I'm not even going to write that because that would be very misleading because derivative is not often average rate of change. But for this particular case, since it's a line, yes, we can find this overall slope. And the slope of the line is the slope at the point. Maybe we could say it that way. So it goes down 20, so our rise over run here. Rise is negative 20 and run is 8. And that would be an acceptable answer. Negative 20 over 8. Units. So you said it was acceleration. So what are units of acceleration? Meters per second squared. Or you can say, you could just leave it like that. I don't know. The way it says indicate units of measure, that sort of indicates that it would like you to do, meters per second squared. But 20 over 8 would be fine. See, if we divided it all by 4, we'd get 5 halves, negative 2.5 meters per second squared. Part B. Let A be the car's acceleration in meters per second. Sort of just gave you the answer to part A, or part of the answer. Write a piecewise defined function for acceleration. Okay, so a piecewise defined function, that's where we got to write it in pieces. So I think my pieces will be 0 to 4, 4 to 16, and 16 to 24. So I might do that first. 0 to 4, 4 to 16, and 16 to 24. And I definitely do not want to include 4 and 16 because we already said those derivatives wouldn't exist. So what's the acceleration between 0 and 4? What's the derivative of this line? Careful, 20 over 4. So 5. It did not specify it as show units, so we wouldn't have to. It wouldn't be wrong if you did, but you could get away without putting them on there. How about the acceleration from 4 to 16? 0. Like that one, you could think about slope, or you could just think, wait a minute, it's got a constant velocity there, so the acceleration is 0. And from 16 to 24, we kind of already found that one. That was negative 2.5. So we wrote a piecewise function for the acceleration. Part C, mean value theorem. Okay, I see mean value theorem. I'm going to just in my brain think that means if it's continuous on the open, differentiable on the closed. Wait, is that backwards? I think it's continuous on the, well, it rarely matters. So if it's continuous and differentiable, that's going to be the issue here. From 8 to 20 is what we're looking at. 8 to 20. Does the mean value theorem guarantee a value for C such that V prime of C is equal to this average rate of change? Why or why not? So between 8 and 20, are we continuous? Is velocity continuous? Continuous just means you can draw the thing without lifting your pencil. It is continuous. Is it differentiable? No. In fact, we already said it wasn't differentiable. So why or why not? MVT does not apply because V is not differentiable at t equals that cusp, 16. Wait a minute. I need to go back and read the question and make sure I answered everything. I jumped straight to the MVT part. Find the average rate of change of V. So I need to back up. The average rate of change of V. So that means V of 20 minus V at 8 over 20 minus 8. So I can still find an average rate of change. It's just, it's not going to equal the instantaneous rate of change because MVT doesn't apply. So velocity at 20 is 10. Just reading off the graph. Velocity at 8 is 20. And 20 might, well, heck, 20 minus 8, just leave it alone. Velocity is meters per second, times in seconds. So there's my answer. I guess I could clean it up a little bit. Negative 10/12 meters per second squared. That's the average rate of change between 8 and 20. Or, yeah, between time equals 8 and time equals 20. So there's our There's our AROC slope. And there's no place that the IROC slope equals that because it's not differentiable. So that's a good free response question from an old AP test. Hopefully everyone would have gotten part A, maybe some of part B, maybe part of part C. Every free response question is worth 9 points. And again, you got to get about a 50 to make a 3, 60 to make a 4-ish. Other questions? Did you want to do one with the position graph?